All right, back to adjacency lists, and where we talked about actual and adjacency. Ooh, hi. Hello. There we go. All right, back to adjacency list. What can we do with the adjacency? Okay, so what operations did we have on the adjacency matrix graph? We had.
Search.
Well, first off, we could ask, are two nodes adjacent? aka.
No. I don't want them to. They're not allowed to be next to each other.
I don't want them.
Where's Carla?
Who's shaking it? Anyways, so if we want to know if there's an edge between 0 and 3, how could we do that?
Look at the graph and see cases.
Can't look at the graph because that doesn't store a data structure. We're only looking at the adjacency matrix. Or list, sorry, adjacency list, which is over here. How do we know if there's a link?
See if there's something
Because
in
there'd be
those.
one in the 3 section.
From 0 to 3. So, I'm sorry, say that again?
You would see what number of your adjacency list is there. Oh wait, that's the. And you would see if 3 is in any of them, and it goes to 0. Never mind. I can't.
No, from 0 to 3.
0, 2, 3.
So where would we first look?
Probably 0.
And
Yeah, so we start at 0 because 0 is holding all the nodes that there's a connection from 0 to something. So if you want to look if there's 0 to 3, you start at 0 and you look at this list. What do you do in this list?
you see the endpoint that it goes to.
Yeah, you search the list, right?
Yeah.
See if there's something adjacent there. How is that different than a matrix? So in here you're searching a list. In a matrix
It just like goes right
You
to
search
it,
for
right?
the array iterators. and
in the
stuff.
matrix you just jump straight to it,
Yeah.
right? Yeah. So it's going to be a little different. Finding an adjacent, if something's adjacent, an adjacency list does cost a little more because you have to search the list. But in general, you hope your lists are small. So that's how you find if something's adjacent. How would you do a depth first search here?
Don't know.
Don't know. All right. I'm going to do something very different and probably kind. That's okay. Maybe it's kind, maybe it's not.
Kindness is good.
So we have lab 23. And in here, as you probably have guessed, we're going to be doing a graph adjacency list. So let me go look up the HPP file. Here we go. This class represents a weighted directed graph via adjacency list. Vertices are given in an index starting from 0 and ascending. Class W represents the weight that can be associated with an edge. We will not weight the vertices. By the way, vertices can contain weight, but we haven't gotten to that. We're not going to deal with that here. So I decided template on W class based on class W, aka the weight, graph AL, graph adjacency list. Struct node. Ooh, what does this mean? What do you think this struct node is holding?
It's holding what would be, if you look at the board, the 0 and the 2, the end version.
Right.
And
So it's holding what this guy is up
Yeah.
here, and maybe another one of these. So we have a node to contain what each entry would be. Great. Then, all right, what's this down here? We have a vector of
lists. Doubly linked list.
so it's a right. It's a well,
Because
no,
you
no.
have to point to whatever.
It's not a doubly linked list. It's a not necessarily. It is technically a doubly linked list, but it's really a vector of lists.
A vector of lists.
Right. So it's not a straight matrix because it's a vector of list, and each list can grow and shrink.
Nope. You can also do two vectors as well.
You could do two vectors here.
But
it-
it's a little weird doing it.
All right. I have some. Let's see, constructor. Let's see. Can I go and look at this? What?
Said no.
Why all the negativity? Oh, right. Look at that. I have some of these already written out. Okay. Do we need to do anything in the constructor here?
It's up to you.
Oh.
Why not? We don't. And that's true. Why?
Because you already declared everything in the header.
So we really declare the vector in the list is basically being created in the header. So we're done there. All right, great. So the default constructor is not hard. Uh-oh, what about if we give you the number of vertices?
Guys, we're doing your lab right now. So, help. Less work.
What is the vertice again?
I'm trying to help you here.
What is the vertice again? I know it's the-
That's a node, vertice node. What's that?
You add a node to the list.
Right. Well, we don't add node to the list. Remember, we have a vector of lists.
So we add to the list.
Vector.
We increase what? The size of the vector. And how do we do that? You know what? Not even I remember. C++ vector.
Pushback?
No. That would be adding to it. But we're adding
Increasing the size. Isn't there an increase
Resize.
resize. There should be a resize.
Yeah, it's right there.
Otherwise, page takes forever to load up.
You know
Hey, it looks
you're
good.
working with C++ vectors so long that you can memorize almost all of
So
them.
resize. So we're just going to go what do we call it? What do I call it here? A list. All right. A list dot resize to the number of vertices. All right. Let's see if we can actually make it. We can. Okay. So that compiled. Looking good so far. All right. So that's how we increase the vertices. We should probably, let's see, take the test. We have empty test. Let's go and test / I don't know, simple al tests.cpp, tab new test simple al. There we go. All right, graph. Oh, with 100. So that gives us 100 nodes for test 1. It's going to do make simple al test. No testify. What's that?
Tests. There's S at the end.
Thank you. Uh-oh.
Yeah,
Oh,
that's
there
the
need-
make file.
Yeah, hold on a second. I misspelled it. Because the way it's written is there needs to be no S. Then you can do make simple al test. There it goes. Tab new test simple al. Perfect. All right. So we have 100. Okay. Probably should be able to add an edge from start to an end. So that would look probably something like gal. Is that okay? All right.
Sorry. I was like, wait, which one's gal? And then I realized you were making.
A graph adjacency list. So we'll probably go from 0 to, I don't know, 4, and we want to give it a weight. We're using integers, so we'll give it a weight of 100. We want to be able to do that, right?
Yes.
Good. So how do we add that here?
The happy trail says a for loop.
Well, what do we first need to do?
Access the
Access
matrix.
the vector. itself.
Okay, so we'll access the vector. You're all thinking ahead of yourselves, but that's okay. MA list sub, which one?
Start.
Start, good. Dot push back. What are we pushing back?
The weight.
No.
And
The list.
Hold on, what is this a list of? It's a list of
Nodes.
nodes. Why is it a list of nodes?
No structs because you have two variables in there.
Right, because we have to keep track of the end vertex and the weight.
Yeah.
So what do we actually need to do first?
make a node.
Make a node.
It's cool.
What's the end vertex? And then what's the last one? Weight. And then we'll push that guy back. Let's see if that compiles. Nope.
Because we forgot to add the true or false.
No, this is C++. It doesn't care.
Alright.
Return true. Alright, so first wrap the end and weight in a node. Now add to the graph. To the graph. Oh, okay. Well, that's good. How would we remove an edge?
Erase. Dot erase.
Okay.
That could be one.
Dot erase. Which one do we erase?
Delete the node.
We have to find it first?
Yeah.
Yes. We need to find it first.
Search.
Alright. How are we going to find the node?
Like picturing conceptually in my head, and then the code comes naturally almost.
What's that?
Is it weird that I'm finding this stuff, like I'm not understanding this conceptually, yet the code is kind of coming natural itself?
That'd be an interesting way of doing it. How do we remove an edge? That's cool. No, that's good.
You go through each of the other edges.
Alright, but where do we start?
That's 0.
Start at 0. Oh, so we start at 0? But do we need to start at 0? Where do we actually start?
At start.
Yes. But so who am I starting? Where am I starting? How do I write that?
And a list, access, start.
Sub start. Okay, there we go. Dot begin. Oh, we got to do a for loop.
Yep.
For, let's see. Oh boy.
STD with
Was it vector of std list? Oh my goodness. Who wrote this?
I've always
I wonder.
You did.
Hold on. It's a vector. Hold on. Hold on a second.
Yeah, my head.
It's actually not a vector. It's a list. So node underscore t
iterator
it equals
MA list begin, MA list
IT.
start end. And then pre-increment IT.
Sure, pre-increment. It actually doesn't matter anymore. It used to back in the day. All right, let's see if that compiles, because I have a feeling the answer is no. I didn't think it would. Is
That's
it
the error
depend?
that I've always gotten.
Hold on. Type really.
It's so dumb.
All right, that was great.
Now put stuff in it.
But now, okay, so what is that for loop actually doing, Caitlin?
First you make some IT, which is an iterator. That's at the beginning. And then you go until it equals the end.
And it's the beginning of what?
Start.
Of what?
The array. Vector.
This camera counts. Of what? What was it starting at?
Wherever you tell it to start.
If start was 3 and we're trying to find the end of 1, where would it start?
3.
Down here?
Yeah.
So it'd start here and go through the list, right?
Yeah.
Okay, good. Just make sure everyone's on the same page.
Start.
All right, so IT represents the current node. So what are we checking?
If that current node matches the one we want to remove.
The end vertex.
Yeah, there you go. So if IT end vertex equals
End.
end. Ooh, I think there's actually a nice way to do this. Iterator, let's just do C++ iterator. Because there should be a remove function. Load. Or maybe there's not. Wow. This is what we want.
Sure.
Alright, it doesn't exist. I thought there was a way to remove it.
I'm sorry, what are you trying to look for?
I thought there was a way to just tell the iterator to remove its current location. I-
back there?
Well, no, I thought that if you were here, you could do something like IT remove, and then it'd be done. But I can't. I don't see it. Okay.
Wait.
Try testing it. Sometimes it could be a little bit iffy.
Wow. All right, we need to come up with a print function here.
Int main.
Hold on, we have something. Do we have a print? Good, we have print. So where's our print function? Do we not have one? We don't. All right, let's go make a print function real quick. So graph al on w print template class w. All right. So how do we print this? Well, let's just go through the list and print it out like real human beings or something. All right, here we go. So for int I equals 0, I is less than m list dot, sorry, a list dot size I plus plus. You do 4. Oh man, we already wrote this, so let's not write it again.
It's already into the second.
What?
It's already into the second.
Okay. Then you go cout the it dot m in vertex comma space it m weight. Put \n. We actually need to start this with a, I forgot my std. I plus, ooh, and we'll put a nice little bar. Let's see if the print function works. Cout was not declared.
Still gonna get errors.
Oh, did I forget to close something? Probably forgot to put a semicolon. All right. Okay, here we go. Well, that was beautifully long. All right. Test runner from blah blah instantiation error conversion from node allocator, wow, to non-scalar type. I had a feeling that shouldn't have worked. So, list of node, because what is it actually? Oh no, it is a list of node. It's right there, list node sub iterator. So what is your problem? List node iterator, begin to end. Okay, let's see what the problem is. It doesn't like the begin. So it's asking to convert from a standard list graph of node, right, to non-scalar type. I don't see the issue here. Oh, okay.
This is an odd problem, isn't it?
Well, oh no. That's right there, so that's not the issue. What is the issue here? From node T, iterator. Okay. We're going to have to dissect this slowly but surely.
Dissecting is fun.
It is. Good. Let's make sure there's one giant issue. All right. Conversion from node allocator constant iterator. Oh my goodness. To scalar type list. Okay, sublist. The problem is there's a difference between what's here and here. So that's match node T, comma standard alligator allocator. Okay. So it's going from a constant iterator
To an iterator.
to a regular iterator. Okay.
You can always do size type.
Hmm?
You can always do do size type.
Size type? What do you mean? This is what it's asking me to do.
Constant size maybe?
Wait, really? Is it complaining about the print function being const? I hope that's not the issue. Wow.
What?
Thanks, C++.
Boo.
Exactly. Boo. There it is. Wow.
That's gonna help you some.
Wow. All right, let's go on.
Just get rid of the const.
Yeah, just get rid of the const.
That's so terrible. All right, so let's not have 10 edges. I mean 100 edges. Let's just have 10. Then we make it. And it's almost printing. Huh. There we go. So 0 to 4. Ooh, that was beautiful. 0 to 4, weight 100. So the question is, can we actually remove it now? Remove edge 0 to 4. That would be amazing. Didn't think so. Wow, I already have depth first traversal written for you. Wow, that was nice of me.
Very, very nice. Thank you.
So m vertex equals end. That's the first problem. And then has no member remove. Maybe it's erase. Nope. It's not delete. All right. So instead, what are we doing here? We got to go back. It's a list, right? Yes.
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 How do we remove from a list? Anyone? Bueller?
You push whatever value you want to the back and then you pop it.
Party hard.
Erase elements. I like where it's going.
Really?
Hey, I didn't make this. Iterator position. Oh. Okay.
Blending tree.
So now you just do ma list substart dot erase the iterator. Yeah, great. Now let's do it. Oh, we had a seg fault. Probably should return afterwards. Return true. Okay. Let's see if it actually, so we print for the removal and we print after the removal. All right, that was it. Of course, that's the loaded question. Was this easier or harder than with the matrix?
I think it was easier. Because you're using STL, which makes your life a heck of a lot easier.
Well, all you had to do for the other thing was just set it to -1.
That's set the bottom to -1. Yeah. All right, how are we doing here? So, whoops. Now we need to have, we don't want to add, we need to find out if two things are adjacent. How do we find out if two things are adjacent?
Scan the vector, or the list itself.
Yeah, so we'll copy this good old for loop down from start to end. All right. Return -1 if we never find it. But if, wow, we can really just,
If the iterator in the end is equal to something within the list, return true.
return the weight,
With the weight.
right?
I thought it was cool.
No, we're getting the weight. Okay, so we really want to adjacent from 0 to 4. This should return should equal 100, right? Oh, good, it's 100. And then if we do it afterwards, it should be -1. Okay, good, so we don't have to print out everything. And now what can we do?
All everything.
TS
Finish our lab.
assert. Oops.
Finish our project.
Oh wow, I can't believe I forgot how this is done. Finish our project, 100, adjacent, 0,4, and then that should do it for us. Yep,
Just have to
Right.
lab until next week.
Right.
right. And then this should actually fail. Make sure we type that correctly. Failure, which is fine. And we'll test that equals -1. What did I just do? Alright, what do I have now, guys?
With magic.
Alright.
Yeah. Your freaking magic.
I create a graph with 10 nodes, I add an edge from 0 to 4, weight 100. Then I test to make sure that I can get 100 back for if it's adjacent.
Bless you.
And then I remove it, and then I make sure that it's now -1. Simple test case. I think someone was saying that they weren't used to how test cases were done here. So here, I showed you how I do them myself. And now that that's been stored, I just copied this test case, and let's go make another one. Test 2.
Crappy pasta.
Mm-hmm. Alright, test 2. What else should we test here?
The other.
Remove vertex, now I'll let you do that. Ooh, depth first traversal. Ooh. 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 Wow, I wrote this all for you. Man, that was nice of me.
You're being very nice.
I really am today. I need to stop it.
No, let's
No,
not.
it's okay. It's fine, it's fine.
It's fine. No, it's good. It's good.
You're good.
We're okay with that.
Alright, depth first traversal. What is this doing? No one? Bueller? What did I do? I created a function called visit. Then I told it to do a depth first traversal passing visit, so I'm passing it a function. And the function just takes a node and just says, I'm at this node. Alright. What else could I do here? 0 to 2. How about from 2 to 3? And I could go from 2 to 5. And then maybe we'll do 5 to 1. If you were to do a depth first traversal on this, what should the order be? If you were to do a depth first traversal on this, what would the order be?
4, 2, 3, 5, 1.
4, 2, 3, 5, 1. Alright, let's see if I can change this up again. How about if I added now what would the order be?
4, 2, 3, 5, 6, 1.
4, 2, 3. You should go 3, then 6, then 5, then 1. Because it's going to go 0 to 4, can't go any further. 2 can go to 2, so say 2, go to 3, 3 can go to 6, pop back up to 3, pop back up to the 2, go to 5, go to 1, pop, pop, pop.
Okay.
Alright, so let's see what it does. Depth first traversal. And we'll pass in visit. 423651. So let's see how this was set up, since I've already nicely done it. First, I can create an array of visited. What is that? Do you think that represents Noah? Noah? Jonah? I have another person called Noah in the other class.
I guess that keeps track of has it been visited. So
Yes.
if it's been visited, it sets it to true.
Otherwise, false.
Otherwise
Perfect.
it's false.
Then we just do the recursive call.
Okay.
If we visited that node, get out, because we're done. Go ahead and visit the node, aka call the function that's being passed in on that node, then mark it as true. Then go through every item in that list and do a depth first traversal on it. Okay. Any other questions? If we want to remove a vertex, what would we do? Hey, look, I have comments. Let's see what it says. What's the first thing you should always do?
Find it.
It's in, I have it as a comment, all caps, with a lot of exclamation marks after it.
Validate the index.
Why am I doing that?
To make sure you're not passing in crazy things.
Would I ever do that to you?
Yes.
I'm trained to know. Oh, that word by heart. That was great. Thank you. I appreciate that.
Don't know if it was a compliment.
Oh, that was a compliment. I took that 100% as a compliment.
Whatever floats your boat.
All right, then what do? Set the index to null. Why would we be doing that? Well, let's go to this graph. Let's go to this picture. Let's say, for the sake of argument, we wanted to get rid of 3. How do we do that in this picture?
Erase it.
Erase the 3. How do we do it over here?
I guess set it to null.
Set this to null. Okay? It doesn't exist. But what else do we need to do?
Get rid of the weights.
I just realized, let's pretend for the sake of argument, we have 2 going to 3 and call it value 4. So over here we'd have to have 3, 4. There we go. Sure. Well, by erasing that, we actually get rid of this edge as well, and this one up here.
Then you would also need to get rid of the 4 weight.
Yeah, this guy.
Yeah.
How would you do that over here?
Set it equal to null.
You'd have to find it first, right?
Yeah.
Because any of these could have pointed to 3. So you start at the top and you have to iterate through every single one of them. If they have a destination to what you just deleted, then you need to remove that edge, which we just had the code for. And then we're done. Right? Okay. All right. So we talked about Adjacency List. I don't think I'm going to ask you to do Dijkstra's here, but I do ask you to do breadth first search. We talked about that last time, so you'll probably have to look up and figure out how you do breadth first here. It's actually not as bad. It's actually fairly easy. It's not that big of a deal. It's just you need to think about how you convert from, how you use an adjacency list instead of an adjacency matrix. It's not that bad. All right. I'm not doing shortest path here, but we will be doing minimum spanning tree, so let me stop the recording here.